Okay, so what we've done so far was a point up to here, mapping to the image plane. We are now taking this step further and move from the image plane to the sensor coordinate system. So mapping to the sensor coordinate system on the assumption that we only have linear errors over here. So what makes a sensor coordinate system potentially different than the original image, the image plane coordinate system? The first thing is the location of the sensor is the main difference. So because the first pixel, or the zero coordinate of the origin of the sensor frame, so the zeroth pixel, is typically not in the middle of the, it's not at the principal point. So there's definitely been shift involved. The other thing, based on the sensor design, I may have a slightly different size of my pixels, so I may have a scale difference among the pixels, and I may have an effect of a shear in there. Let's start with the sensor system. So the principal point, xh, sitting over here with the x and the y axis in the coordinate system of the image plane, but my sensor starts somewhere over here. Because I don't want to let the sensor start here, I would basically lose the information about this part of the image. So this is the origin of the sensor coordinate frame, so typically that over here would be the pixel 0, 0. In order to compensate for this is a simple shift. Just in our pixel coordinates, so in the 2D world, can be expressed with this transformation just by shifting the element by the x and y coordinate of my principal point. Okay? So in case we have a scale difference in x and y, just put on the main diagonal 1 and a 1 plus m, so m basically tells me the difference in the scale of both, and I may have an effect of a shear in there, although this is typically 0 for all digital cameras. Well, it takes values around 0, so in reality this value should be somewhere around 0. So with that, we again can say this was the system that we had so far, the transformation that we had so far. We add this additional transformation here having 4 parameters, 1, 2, 3, 4. And in a lot of cases, s is 0, and often m is also 0, then it's often just, let's say, this is then what is called the Euclidean camera, the shift only through the sensor plane. What I can then do, I say, okay, I can now define a new calibration matrix, because these are definitively parameters which I would associate to the camera and to the camera setup. So I can combine this calibration matrix with this transformation and define a new calibration matrix, which is just the product of those two matrices. This one was a scaling through the by the camera constant, and this is exactly the transformation that we have here. So just by combining that, so taking those two matrices, multiplying these two matrices, this is the result that I get, and this is the standard calibration camera for what is so-called the affine camera. So a camera which, with a mapping from the image plane to the sensor, is an affine transformation. And this is a standard model for the cameras having 5 parameters, 1, 2, 3, 4, and 5. And so therefore it gets an extra slide. It's called the calibration. This calibration matrix is an affine transformation, and therefore the camera with following this calibration matrix having no nonlinear errors, something that is called the affine camera. And again, we have our 5 parameters over here. If I describe that mapping, then how a point is mapped with this calibration matrix from the 3D world to my image point, there's something which is also called the direct linear transform. This is kind of the transform from the world coordinates to my sensor, assuming nonlinear errors. And it has 11 parameters. These are the 6 parameters of the Extrinsics, or Äußere Orientierung, and 5 parameters for the intrinsics for the innere Orientierung. Again, so saying that the term affine camera, read that with care. So it basically means that the transformation or the mapping from the image plane to the sensor coordinate system or to the sensor frame is an affine transformation. We still have the projection from the 3D world to the 2D world in that camera through the central projection. And they are mapping from a 3-dimensional space to a 2-dimensional space and have a loss of information, because in a affine transformation you can typically just invert by inverting it. But this inversion only holds for the mapping kind of done inside the camera, so from the image plane to the sensor. Direct linear transform, as I said, has these 11 parameters. I think I just said that. And it's also the name for this model, and it's also a name for a technique on how we can actually estimate those parameters. The technique on how to estimate those parameters, given some known points in the environment, is actually something that we're going to do next week. So for the lecture today, we're just taking all that into account and just setting up the model, how does the mapping work, and then next week we actually focus on determining those parameters for a real camera. Again, we can also do this mapping in the Euclidean world. This basically boils down to the projection matrix taking into account the rotation and the calibration elements, and then this would be the mapping using the full matrix over there. So I guess what's missing over here is the subtraction of the...
That S in the formula is different from the S from the shear factor, right?
So this S is just the index, it's a sensor system. Yeah. Okay, so this part is done. Let's look into the nonlinear errors. So I told you so far, we just modeled the linear effects, but if I'm talking about linear effects, there should also be the nonlinear effects. And this is everything which goes beyond the DLT, and reasons for those nonlinear effects are typically things like, as I said, an imperfect lens. This has a strong effect. If you simply have a fisheye lens, where straight lines are not mapped onto straight lines anymore. This is a nonlinear effect that I have. Or things like if the sensor is not perfectly planar, and other effects which cause nonlinear errors in here. So we're now looking to the nonlinear error, so we're in the last step of this chain of transformations. We are still staying in the sensor coordinate system, but we want to map kind of a nonlinear change in those pixels. And this is kind of a general mapping, which means that every pixel, in theory, could be mapped to a different pixel location. And this is a transformation which is individual for every pixel, so it's kind of a shift in every pixel. Every pixel is shifted to a different location, and where it's actually shifted to is independent, or can be independent for every pixel. So the general mapping is location dependent, so that from XS, which was the solution I had before, I get a shift in X and a shift in Y, and this depends again on my X location and some other parameters. So in theory, I could see that if I describe this in this way, it's done as a very general mapping, I can basically remap the location of every pixel to any other new pixel location. Of course, typically I describe this as a parametric function, but as is written in this way, I can have a special mapping for every individual pixel, that this should be actually at a different location if I would compensate for the lens errors. So this location is typically the location in the image plane, this X, where the point is mapped in my image plane or in the sensor plane, but with respect to the principal point, at least how this is often described. This has an impact on the transformation. So depending where the point is mapped to, I actually change it. So if a point, for example, is mapped directly to the principal point, I may not want to change that. But if a point is 10 pixels away from the principal point, I may want to move it closer or further away from the principal point. This is one of the examples that we'll see in a second. So this is an example for a regular camera image, which is non-calibrated. And what we see here, that straight lines are not mapped to straight lines. So because this keyboard is actually a straight line in reality, but as you can see here, this is not a straight line, so it's a curve. And there's a typical effect that you have from, for example, a wide-angle lens. What we now want to do is we want to perform a correction, so remapping the location of the pixels, that we can actually compensate for this effect. And this is exactly what has happened over here. Here, we've done the calibration. Here, this is mapped to a straight line again. So there's some black areas like down here, here on that side, up here, maybe even here. And these are simply locations for which I do not have any information because they were lying outside of that image. What you can also see from just the black areas, how they are shown here and here and here, it seemed that it's kind of you punched into the image here and moved everything a little bit more in the inside. Also here from the left-hand side, not sure if this was cut or it's more from the right-hand side, and also in the middle. So it seems to be something where there is no shift or no transformation in the center of the image, and the further I go to the outside, the more the pixels actually moved towards the center of the image. In here, in X and in Y. This is just one way for doing such a correction. So if I have now my general mapping, I can express this as a general mapping that I had before. So this is the point in the sensor frame. So what we did so far up to the DLT, we are here. That's the result of the DLT. And now we have this additional mapping, which maps me to something which, although it's kind of the same coordinate system, I just called it with the superscript A to indicate, to differentiate those variables before and after the transformation. So if we put all that together, we have this transformation, which handles nonlinear effects, and those which handles the linear effects. And the key thing is that this depends on the output of the mapping over here, because it's individual for every pixel. I can also, of course, combine those two transformations. If I've combined those two transformations, so multiplying this transformation with the calibration matrix for the affine camera, I had exactly the same matrix over here, like this was the calibration matrix of the affine camera. And then I get two additional correction terms which basically shift the pixels away on a pixel-dependent manner. So the question is now, how do those functions look like? And there are different ways for doing that. One is kind of, or there's several ways for doing this, but kind of two classes of approaches. One is an approach which is motivated from physics, where I really try to describe what physical effects can cause shifts in pixels, so where pixels are actually mapped to. Then I need to try to account for all the errors I have in lens, which we discussed at the beginning of the course. And I may need a very, very large number of parameters, which are kind of tricky to approach in order to estimate this effect. Or another approach where you say, okay, we are not really interested in exactly modeling what's going on in physics. We just fit the model, estimate the parameters of those models, which describes the correction, and are happy with that. This is typically easier which can be done easier, but I don't necessarily understand which effects cause my problems. Just fit something in it, and it fixes the problem. So this one is nicer to do, but it's more complex. You have different effects which may even compensate for each other. So it's actually a non-trivial job to do that. One example for just checking or just fitting a function and hoping of getting rid of the effects that we can actually see over here is something I can do for a barrel distortion. So I do a mapping of an image point. So this image point, which is the point after the ideal pinhole projection. Then I say, okay, I just shift this point And the key thing is here this factor r, and the factor r is the distance from the principal point, so from the center of my image. It's perfect. So the center where the viewing direction of the camera hits my image plane. This is also the fact the further I am away from this principal point, the larger this correction will actually be. And this is something I can use in order to, for example, compensate for the barrel distortion. So what I have in this, I have kind of, so this value r is different for all the pixels. It's the distance from the principal point. And this q1 and q2 are the two additional parameters of my nonlinear function that I actually have to determine. So what I would need to do if this is my model for the nonlinear corrections, I have to determine these parameters q1 and q2. But what we can have is if we now kind of look to an image, and this is kind of for example, for the barrel distortion. So let's assume this is the function of the barrel distortion over here. So this is kind of how far am I away from the principal point, and what's the amount of the distortion is. So you can see here the distortion is small, and the further I go to the outside world, the larger the distortion actually is. Just shown by those arrows over here. But one thing to note is actually this linear line over here is also something, it's kind of the linear function depending on how far I'm away. This is strongly related to actually the camera constant, because this camera constant does a scaling of the points. It also scales them how far they are away, the x and y coordinate from the principal point. If we go back to the equations that I wiped out that had been here before, we always had this factor c in front of it. So if I kind of compensate for that and then estimate a different radial distortion, so radial distortion is like this line gets compensated by the camera constant. So a change in the camera constant also leads to a change of the radial distortion. So there's a dependency between the different parameters, also the linear ones in the DLT, and the potentially nonlinear parameters. But again, I can specify such a model like for the barrel distortion with additional parameters, and then I need to find a way for estimating those parameters. And one way for doing this is I place an object in front of the camera where I know the geometry of the object. I take images of this object in different locations, and then trying to estimate a transformation so that all the distortions go away. For example, using a least squares approach. It's one way for estimating those distortion parameters. I don't want to go exactly in the details how such models could look like. This was just kind of one small example, but more, again, discuss how the mapping process looks like. So the overall mapping that we have for kind of our general camera, including also nonlinear errors, can now be seen as a two-step process. First, we do the projection according to the DLT. So we map from our world coordinate system to the sensor coordinate system without modeling only the linear effects. So this is the model of the fine camera. And then, as a second step, we have this XS over here. This influences, of course, the X and Y coordinates over here, which affect the transformation and then give the final result. So this parameter can, for example, be this radius r, which depends on how far that point is away from the principal point. But it's something which depends on the pixel location from the projection. Yeah, that's also, and basically what I said. So the important thing is that this is point dependent and depends on the point. And this is how this mapping typically is done. So we have this fine camera step. This result is then in some way influences this function over here, for example, by the distance to the principal point, and this gives a new location for that pixel. Okay? So what we have done now, we kind of we looked at the image, have the image in mind. We had in the beginning through all the coordinate system. We're now here at the end. So what we now want to do is we want to turn around and say, okay, given that we have such an image, what do we know about the scene? So can we actually go back and end up being here again? So it means we need to invert the mapping. So our goal is to invert the mapping from XA and go back to the point in the 3D world. We can again do this as a two-step process, the same as we did it before. The first step is to map from A to the sensor coordinate system. And then once we are in there, we can, for example, invert the fine transformation. And we have this projection there where some information is lost, and we need to see how we can actually handle that. Okay, let's start with the first step. We're going to go from A, from the location, taking into account the nonlinear effects, back to the mapping in the sensor frame. So the problem is that this transformation here, it actually depends on X, so I cannot easily invert that because I don't know the input value. I only have the output value of that function. And since this function depends on this X, I cannot directly invert the function, but what I can do is I can actually solve this through an iterative process. Under the assumption that this transformation doesn't kind of rearrange the pixel, they all kind of stay in their local neighborhood. I can actually try to, with an iterative approach, to invert that. So that means I simply start saying, I simply assume this X is the location taking into account the nonlinear errors. I just start with that. I put that in there, calculate that matrix, and then I simply invert that matrix. And then multiply it with my input point. And this gives me a first estimate of my location X in the sensor frame. At least the hope is it goes a little bit more into the direction of that S. Of course, this strongly depends on how H looks like, but for most realistic functions, the correction is not too extreme. That actually works well. And then I simply iterate this process. I take this value and feed it again in here, and repeat the same process, always again and again. Here we always keep XA. This is the input value to our function. So we iterate this process until we basically have no change in this transformation. And quite often this actually converges quickly. The only thing I need to take care, and so this point here is typically parameterized with respect to the principal point. We need to make sure how this is parameterized, like whatever the distance from the principal point. So it's kind of a slightly sloppy notation that I just put that X in here, but I think it's clear what I mean, that I don't parameterize it with respect to the point I get from the direct linear transform, but I parameterize it according to my starting value, or then the iterative value. So is this idea clear? Basically iterate this process until nothing changes anymore, and I said, okay, I'm hopefully found my transformation. And as long as H is not a completely random transformation, that's actually going to work. Or, of course, you find transformation where it's not going to work, but for those that we typically experience with cameras and calibration there, this approach works. Okay, now we need to go to the second step, which says we are now in the sensor frame, so we now ended up being here. Now want to go back to the real world. The problem was that we had that projection there, so we lost the dimension. How can I actually recover that? We can't recover that point, but we can at least recover the direction on where this point must lie. So we can recover a line through the 3D world and say the point must lie on this 3D line. That's something which intuitively matches what our understanding of the image acquisition process. Any point on a certain line is mapped, like here, whatever, my laser pointer. Every point which lies on that line is actually mapped to this image point. Let's see if we can use the mass that we have so far and see if we can recover that. So the first thing we said, okay, my point in the sensor frame, here, S, well, this point in the sensor frame, is the projection of the point in the original frame, in the 3D world, which is this equation over here. As we are using homogeneous coordinates, I can actually multiply this with an arbitrary factor over here. Okay, so to be more clearer, so here should be actually a superscript S. Okay, and I can say, okay, that's fine. I can simply rewrite this variable here as a homogeneous vector consisting of my Euclidean vector and my 1 over here. Right? It's the definition of the Euclidean vector. So if I multiply now this matrix with the Euclidean vector, I actually get this equation over here. Just multiplying this. So it's kr times x minus kr x0 times 1. So this stays the same. So this is now the equation that I have. Again, the factor is something, it's just my scaling factor from my homogeneous coordinates. So now do I take this equation, copy it to the next slide. So we start from this equation over here. What I can do now, what I now want to do is I can move this block here to the other side and multiply from the left-hand side with kr to the power of minus 1, to obtain my vector x. So this is my vector x in the Euclidean coordinates. Then the remaining part is this block over here. So move to the other side, multiply it with kr to the power of minus 1. This was this part inverted. And then plus lambda kr to the power of minus 1x, which is this block over here. Okay? Everyone happy to here? Okay. So then, that's easy. Those cancel out. So this is just x0. Then I have a scaling factor lambda, kr to the power of minus 1, and my image point x. And we said this is an arbitrary value. So what we actually have in here, if you look to that carefully, this is actually the equation for a line, or a straight line. Starting point of the line plus the scalar. This gives me the direction where the line goes to, and this depends, so all this gives me direction. So the parameters of my camera and where the camera is looking to, and which pixel I'm actually considering. So this block over here, the whole block, including the x, describes the direction of the ray which passes through my image point. So just with kr inverted times the pixel coordinate, I actually obtain the direction in which the point lies in the 3D world. So I can actually invert the process. The solution that I get is a 1D solution space, and this corresponds to a straight line, and I can compute all the parameters of this 1D solution space if I know the extrinsics, which consists of x0, so the location of the origin, and the rotation matrix, and if I know the intrinsics encoded here in my calibration matrix, and of course the pixel coordinate. Once I have that information, I can actually recover this straight line on which the point in the 3D world actually lies. Okay? Kind of clear how that works? Whenever you have an image, you want to know what the ray that corresponds to a certain pixel. The only thing you need to know, where is this camera in the real world, and you need to know the calibration matrix, and then you can actually compute that line. So, how does this change if we move away from digital cameras and go back to the analog world? Just for having mentioned that, the process is actually very similar for analog cameras. The only difference is that this shear component is typically not 0, as it is for digital cameras. And one other thing, if I want to make those cameras and then use a measurement device, for example, those old devices you see there in the background, which you use to analyze aerial images, those on the lower shelf on the right-hand side, you actually use so-called fiducial markers or Randmarken in the images which are taken in order to establish a connection between the additional coordinate frame. And if you look to those things, this is an aerial image, sorry you can't see that well. Down here are markers. This markers kind of zoomed in looks like this, so there are multiple of them over the image. Here's another one, there's another one over there and over there. Then you can actually use those to fix the coordinate system for when you analyze those images. And the same holds, so different companies have different fiducial markers. There's another small one over here which sits over here. You have them here, here, and here. And so you use this to establish an additional coordinate system for doing your measurements. But the overall process of calibrating those cameras is actually the same. Well, yeah, it may have different effects, and can you imagine if you have a film in there running a film, you may have different effects, and if the film gets older, it may deforms a little bit, so you have more problems typically if you work with analog cameras. But just want to make that connection that you can do a very similar process. Also for analog cameras, you may need to take different errors into account, like whatever, how old is the film, how was it stored, was there any deformation of the film, or was the pictures actually taken on glass pane, on glass to avoid this, what you have with standard films. These are all things you may need into account if you go back to analog, if you would do that for analog cameras, but I have never done that for analog cameras. I think you will have to do that for analog cameras as well. Okay, this brings us towards the end of today, and we can actually then shortly classify what kind of cameras do we have. So these are all the different parameters listed over here that we identified so far, starting with the extrinsic parameters, the intrinsic parameters, the linear intrinsic parameters, and the nonlinear intrinsic parameters. And if you have a camera which only determine the position of the camera in the space, and the rotation matrix is identity matrix, something which is often called normalized camera. Again, you have the description of the pinhole camera, where the principal point is the origin of the image coordinate frame, and the x and y axis of the image coordinate frame is aligned with the x and y axis of the world coordinate frame, and the distance between the origin and the image plane is 1. All the constraints you need to take into account. And the rotation matrix plus 1 comes from the alignment. They can say, okay, now I want to add a rotation matrix. So I move my camera in the space, now I want to rotate it as well. There's then something which is called the unit camera, which is actually the perfect pinhole camera where the distance from the, where the camera constant is 1. Because then we don't have that additional parameter. So the distance from the origin of the camera to the image plane is 1. You say, okay, now I can actually add that camera, this constant, if it's not 1. And then I actually end up having what's called the ideal camera. That's something actually I pointed out during the presentation today. When we just do the perfect ideal perspective projection with the pinhole model, we only have the camera constant, everything else is perfect. Then we have our ideal camera. And it uses the parameters up to here. As soon as I have a sensor and the origin of the sensor is not in line with the origin of my image plane, which will be the case for any reasonable application with a digital camera, otherwise you would lose 3/4 of the image map to the image plane. Then you have something which is called the Euclidean camera, which basically consists of just shifting the sensor. And then finally, we take the two other parameters into account. Also, the shear is often 0 for digital cameras, so it takes values around 0. This is what's called an affine camera, and an affine camera is still a camera that preserves straight lines. So the example with the keyboard we have seen before, this was not an affine camera because we had these nonlinear effects, which we then tried to compensate for. And in the end, we have the general camera, which takes 2, 3, 4, 5, an basically arbitrary number of parameters into account in order to do that mapping. All those cameras have different calibration matrices, and the calibration matrices get more and more complex in the sense that more and more parameters are involved. We start with a normalized camera or a unit camera. No, yeah, normalized camera is even not here. We have the unit camera, because the unit camera and the normalized camera have exactly the same calibration matrix because they only differ with respect to the rotation, which is not part of the calibration. So then the calibration matrix is the identity. The overall mapping process has 6 parameters for the unit camera and 3 parameters for the normalized camera. If we move to the ideal camera, that means we have a camera constant. We get 1 parameter more. And let's see on the main diagonal, the Euclidean camera is a camera with a shift. Then we have the affine camera, now having 11 parameters. And then we may have 11 plus n parameters, and the n handles those nonlinear functions in here. Just in terms of naming, if we have a camera where the intrinsics are not known, so I don't know anything about those intrinsics, it's typically an uncalibrated camera because I don't know the calibration matrix. If I know the calibration matrix, the camera is typically got calibrated because I have those calibration information. I can apply that to correct my image. And there's actually an old term which is frequently used in German. It's called Messkamera. In English, maybe would translate as metric camera. This is basically a calibrated camera where the calibration never changes, which is a very ideal situation. So even if you take whatever expensive cameras, and you take those cameras on an airplane to take aerial images just by the difference of temperature, unless you heat the cameras, always keep it at 20 degrees, you will experience effects in the changes, for example, of the camera constant, which then has an effect on the camera calibration. In the process of determining those parameters, especially the intrinsics, something which is called camera calibration. And we will look into techniques for estimating those parameters next week, or next Tuesday, and discuss an approach start with an approach for estimating all the elements involved in the DLT, so the exterior orientation, as well as the 5 parameters for the interior orientation of the intrinsics, to determine those parameters given that we know the location of some point in the 3D world. So given we know where some points are in the 3D world, I can actually recover the other information. And then, depending on the time we have, we also look into camera calibration, seeking for only estimating the intrinsics, but also taking into account the nonlinear effects. But the question is how much time we're going to have for that next week. That's the question. And in the okay, I will come to that in a second. So to summarize what we have done today is we looked into the process of how do we get from the point in the 3D world to the image on my chip. We also showed at least we spent a short amount of time on how I can actually invert the process, but we could actually show that we can recover this 1D solution space once we know the calibration matrix and the extrinsics of the camera. Yeah, that's basically what we have done. If you should summarize the whole lecture with a single slide, I would probably use this slide. We have these different coordinate frames. We have the rigid body transformation, which corresponds to the extrinsics. Then we have the central projection, and an affine transformation, and potentially nonlinear effects, which refer to the intrinsics. We have the mapping from the object system to the camera system. Then the projection, this is the stuff where I lose one dimension, to the image plane, to the sensor, and then taking into account the nonlinear effects. So what comes next? As I said, camera calibration is something I want to look into. So estimating the intrinsics, estimating the position of the camera given I know something about the 3D world, and then maybe even estimating the camera location or the location of objects in the scene once I know the camera parameters and know where the camera is. So that I can start to think about where the camera or where are objects. And we will start with putting known objects in the world, assuming we know something about objects, and then see what we can actually get to know about the camera. So this can be just the location of the camera and its orientation, but it can also be the intrinsic parameters. And with this, we will probably finish the Photogrammetry I course in 2 weeks. And then in the Photogrammetry II course, we'll also look into the other problem. So what do I know about the orientation of the camera, and what does this allow me to tell about the location of objects? What happens if everything is unknown? We can actually show that we can also recover information about the geometry of the scene and the location of the camera from multiple images based on this mapping process that we have seen here. So that's it from my side. Again, Wolfgang Förstner script is a pretty good reference for all the material that I have. It's from the notation pretty much in line with what's in the script. I fixed a few number of index errors here on the slides. They should be also updated on the script, but there's some minor things. And if you want to even have a more in-depth treatment, I recommend the Photogrammetric Computer Vision book, also by Wolfgang and by Burgard and Wrobl, which has a much more in-depth treatment than what I've done here. That's it from my side. Are there any questions from your side? So my hope is that you have understood we map from the 3D world to the sensor, to the pixels that I have in the end. And what information I know about the scene if I map back. You should know about what are the extrinsics, what are the intrinsics of a camera, and that they understand that there are nonlinear effects which can cause deviations from my affine camera model, so that, for example, straight lines are not straight anymore. But if I have an appropriate model for those effects, I can actually know those parameters, I can actually compensate those effects. That's it from my side. Thank you very much for your attention and see you next Tuesday. Thanks.